Hello, this is geometry lesson 5-5, inequalities in two triangles. This is the last lesson of this topic. In this lesson, we'll be able to compare a pair of sides of two triangles when the remaining pairs of sides are congruent. Okay, let's look at explore and reason. A woodworker uses a caliper to measure the width of a bat to help him determine the width for a new bat. The woodworker places the open tips of the caliper on the bat. The distance between the tips is the width of the bat. Okay, so we got some relationship between a width of the bat and the distance between the tips. All right, suppose a caliper opens to an angle of 25 degrees for one width of a bat and opens to an angle of 35 degrees for another. What can you conclude about the width of the bat? Okay, we know that the distance between the tip is a width of the bat, right? This is the width. So if it opens at a 25 angle here, and then it opens 35 angle over here, how are the widths how could the widths change? Because the angle is opposite to the distance between the tips, we can use theorem 5-10 and 11 and say, oh, 35 is greater than 25. So the side opposite to 35 degrees must be greater than the side opposite to 25, right? Which means the width of the bat is greater for an angle of 35 than the one for 25 degrees. Okay, so let's record that. Let's write that down. The caliper opened to an angle of 35 degrees for the wider parts of the bat. Part B. Next, suppose you use a caliper to measure the width of a narrow part of a bat and a wider part of the bat. What can you predict about the angle to which the caliper opens each time? So whenever the caliper opens a larger angle, would be the wider part of the bat. Okay, so make a prediction for the general measures of bat. The caliper will open to a larger angle for the wider part of the bat. Let's record that. All right, so in this lesson, we'll think about this big essential question. When two triangles have two pairs of congruent sides, how are the third pair of sides and the pair of angles opposite the third pair of sides related? So mostly we'll think about the third side and their pair of sides and the angles of that. Let's look at example 1. Investigate side lengths and triangles. As a rider pedals a unicycle, how do angle A and length B change? What does this suggest about the change in the triangle? So if you've ever have seen or have ridden a unicycle, it's like a bicycle, except you just have one wheel and you're just gonna balance yourself on one wheel and you don't have anything to grab on. And it's fun, it's more compact, easy to carry. Yeah, let's look at this problem, right? So the C post is here, and it's related to the center of the circle. And whenever side B increases, the measure of angle A increases, right? This is the initial angle. And then it's going to go around. So the angle here, the blue part, is going to increase. And that means the distance between the side post and that that part of the crank arm would increase, which is represented by B. Because if two sides of a triangle stay the same, the measure of the angle between them increase when the length of the third side also increase. Okay, so let's look at try number 1. Let's compare the measure of angle J and side length K for the triangles. How would side length K change looking at different angles? So this is acute angle, and that's going to be less than 90 degrees. This is a right angle, so J must be right, like 90 degrees. Obtuse is greater than 90 degrees. So if this J is less than 90 degrees, which is opposite of line K, of course, line K must be shorter than the right triangle. And the obtuse is the greatest angle of them all. So K must be the longest in the obtuse, right? So you can say that measure of angle J increases as the length of K increases. And the triangle goes from acute to right to obtuse. So you can say acute is smaller than obtuse. Wait, right and right is smaller than obtuse. Both for the angles of J and the measure of K. All right, so that's theorem 5-12, Hinge theorem. If two sides of one triangle are congruent to two sides of another triangle, and the included angles are not congruent, then the longer third side is the opposite of the larger included angle. Ooh, we cannot prove that the triangles are congruent, but we can use it as an information that, oh, the third side of this triangle would be greater than the other triangle because the included angle is greater. Okay, so we're not trying to prove that the triangles are congruent. Just remember that, oh, we just need to know the opposite side would be greater than the other third side of the triangle if the opposite angle would be greater. Example 2, apply the Hinge theorem. The tension of the exercise band varies proportionally with the stretch distance. The tension T is described by the function T of X is equal to Kx, where K is a constant that depends on the elasticity of the band and X is the stretch distance. Which position shown in the figures has a greater tension in the band? So first, you can model each figure with a triangle. This triangle has a smaller degree between the person's body and the arms. And this triangle has greater angle between the person's body and the arms, right? And so draw those two triangles here. And then you can figure out if they're, and you figure out the calculations, and then you can compare them. T of LK is the tension when the angle is 50 degrees. Okay, the opposite side. And T of MK is the tension when the angle is 80 degrees. Since 50 is less than 80, you can apply the Hinge theorem and say, oh, tension is going to be greater for the opposite side of 80 degrees than the 50 degrees. So it just sounds hard because the concept of tension is not familiar with you, but you can apply the Hinge theorem into the tension of the elasticity band like that. Okay, so let's look at the trial number 2. The man keeps his arms extended and the length of the tension band is same. If he wants to make the measure of angle L smaller, how would line JK change? See if you can do this by yourself. Think about it and come back when you're ready for answers. Okay, so you can see that JL and KL do not change, but JK will change and the angle L will be changed, right? If it gets smaller, of course, the side opposite to that would get smaller as well. So JK will also change according to angle L. So as the man bends his knees, what happens? Measure of angle L decreases as JK decreases. Okay, so a common mistake, common error for this problem is that you may think that line JK should bend, like it couldn't be a straight line, as the man bends his knees because your body could maybe like bend a little bit, right? But you need to understand that JK is not a scale model of the man's torso and legs, but it represents the distance. So that's not the man's body. It's the distance between his shoulders and the feet. And the distance is always perpendicular to the ground from his shoulders and the feet, right? So JK will always be a straight line between J and K, okay? So it's not gonna bend or anything. It's gonna be a straight line. And also think about how the Hinge theorem and the SAS theorem are alike and different. I'm actually gonna write that question down because it's important. Please write it as in your notes. Okay, here's a note for JK representing the distance between the shoulders and the feet. And also, how is the Hinge theorem and SAS theorem alike and different? They both apply when two triangles have two pairs of congruent sides, right? So we do have two congruent sides as an information. But for the Hinge theorem, what's different? So included angles are not congruent. The Hinge theorem gives the relative size based on the length of the third side. So we're not necessarily proving the triangles are congruent using the Hinge theorem. And for SAS, the included angles must be congruent so that we could prove the two triangles are congruent, okay? We need to keep that in mind. Hinge theorem is not for proving triangle congruency. So I wrote down that they both have two pairs of congruent sides given as a given information, but the Hinge theorem does not have the congruent included angles, like does not have the fact that the included angles are congruent. And it gives the relative size based on the length of the third side, okay? So it's a relativity. We're comparing the triangles. But SAS must have the given information that the included angles are congruent, and SAS is for proving the triangles are congruent. That sign is for congruency. Okay, so please keep that in mind. Theorem 5-13, converse of the Hinge theorem. So converse is flipping the hypothesis and the conclusion, right? So now we're gonna say if two sides of one triangle are congruent to two sides of another triangle, and the third sides are not congruent, then we can say that the larger included angle is opposite the longer third side, okay? So example 3, prove the converse of the Hinge theorem. We're gonna use indirect reasoning to prove the converse of the Hinge theorem. So if you're given that the two corresponding sides are congruent and that EF is greater than UV, we want to prove that angle D is greater than angle T. So first we're going to assume that this angle D is not greater than angle T here, which means we can assume that D is equal to T. We would have to assume later if D is less than T, okay? But we're gonna start with D is equal to T. Oh, or it says D is less than T, okay? So assuming if they're equal, then the angles must be congruent. So by SAS, the triangles must be congruent to each other, but we're given that EF is greater than UV, so it's a contradiction. The corresponding sides must be congruent, but they're not. So this contradicts EF is greater than UV. Let's complete the proof of the Hinge theorem. We did not prove the entire thing. We need to prove this part, okay? So assume that angle D is less than angle T, and that it leads to contradiction of the given statement, EF is greater than UV, okay? You can use the theorems that we just learned last lesson, or just this lesson, the Hinge theorem. You can use the Hinge theorem. Okay, so first step, assume measure of angle FDE. I know I abbreviated as D and T, but because the problem says so, we're going to use this. By the Hinge theorem, EF is less than UV, but EF is greater than UV by given. So angle FDE is not less than angle VTU. Since neither the statement that D is equal to measure of angle T, nor measure of angle D is less than measure of angle T can be true, what can we say? Measure of angle FDE must be greater than measure of angle VTU. Which proves the converse of the Hinge theorem. There you go. Okay, now that we proved it, let's apply the converse of the Hinge theorem. So look at this figure here. What are the possible values of X? Okay, so if we know that BC and EF are congruent and ED is also congruent to those two, and all these sides AC, CE, EG are congruent to each other, we have two congruent corresponding sides that are congruent to all these triangles. So we can look at the included angles, 60, and the opposite side, 21. Okay, we have 18 here, and that angle is 2x minus 4. And we have 14 here, and that angle is 36. So obviously, the longest side is 21, so 60 must be the greatest one. 18 is the next longest one, 14 is the shortest. So 36 is the smallest side. So 2x minus 4 must be less than 60 and greater than 36 in order to match 18. We don't have to figure out the exact number, but we can say, oh, X must be between these two values, okay? So write the inequality like we did last lesson and say, oh, 2x minus 4 could be greater than 36, must be greater than 36, and must be less than 60. And then solve both inequalities at the same time. You add 4 on both sides, all the sides actually. And then 36 plus 4 is 40. 60 plus 4 is 64. Divide 2 on all the sides. 20 divided by 2, 40 divided by 2 is 20. 64 divided by 2 is 32. So we know that x must be greater than 20 and less than 32. Okay, those are all possible values of x. So applying the Hinge theorem and the converse of Hinge theorem, what are the possible values of x for each diagram? Try number 4. See if you can do it by yourself. Come back when you're ready. You need to have inequalities as your answer. You can't just have one answer. You just don't know. Okay, so part A. These two sides are corresponding, these two sides are corresponding, and they're congruent. So, which means the included angle 54 and the opposite side 12 must be greater than, in comparison to this side, must be greater than this triangle, right? So 12 is greater than 10, and 54 must be greater than 4x minus 18. Do we have a minimum value? Not really. But so let's start. Wait, yes. I mean, it must be greater than 0, right? So 54 must be greater than 4x minus 18. And this angle cannot be 0 degrees in order to get a triangle. You need to have at least 1 degree or 0.1 degree of anything greater than 0, right? So this must be 0 degree, right? So then you solve for the inequality, add 18 on all sides, and then you get 72 degrees here, and 4x, and that's greater than 18. Okay, and then you divide 4 on all the sides, and then you get 18 is greater than x is greater than 4.5. And so what is your possible value? What are your possible values for x? X must be greater than 4.5, so that makes a triangle, but less than 18. Okay? Commonly made mistake. You might just skip the minimum part and say, oh, x must be greater than 0. But no, your expression here must be greater than 0. X doesn't represent your entire angle, right? So you need to put the entire expression greater than 0 and solve for it. Okay, part B, in a similar way, you're gonna apply the converse of the Hinge theorem and say, oh, look at this line. This, by reflexive property, this line is congruent to itself, and these two lines are congruent. So the included angle must be relative to the included angle here and the sides, right? So 16 is less than 21. So we know that 32 must be less than this angle, 3x plus 5. Okay. And this cannot be greater than what? 180 degrees. But for this one, let's not worry about the maximum, okay? Yeah. Actually, why don't we say that? It must be less than 180 degrees. In order to make the triangle. Okay, so then we're gonna subtract 5 on all different sides. Say, oh, that's going to be 27 less than 3x less than 1 53. Okay, and then divide 3 on both sides, all sides, and 9 must be less than x, must be less than 153 divided by 9 is 17. 17. So x must be greater than 9, but less than 17 in order to make a triangle. Yes. Okay, so that was try number 4. Let's summarize our lesson. In summary, we had these two theorems, Hinge theorem and the converse of the Hinge theorem, and they compare the two triangles using the included angle and the third side when we have two corresponding sides that are congruent. Okay, so that was lesson 5-5, inequalities in two triangles. Congratulations for finishing the topic. Let me know if you have more questions in class. Please ask Ms. King if you have more questions. I'll see you in the next topic. Bye.